Thank you, Lane. Our next speaker is Dr. John Nielsen Gammon. Dr. Nielsen Gammon is the Texas State Climatologist, Director of the Southern Regional Climate Center, Director of the Texas Center for Climate Studies, and a Regents Professor in the Department of Atmospheric Sciences at Texas A&M University. Dr. Nielsen Gammon has received many awards over the years. He is a fellow of the American Meteorological Society. So please join me in welcoming our Texas State climatologist, Dr. John Nielsen Gammon.
Okay, so my presentation is titled Drought Challenges for Texas Water in a Changing Climate. Now, drought is always a challenge for Texas water, unfortunately. I'm going to focus on the changing climate aspect of it, which is an add-on to the issues that everybody always has to deal with already with respect to water. And when it comes to climate change, it's easy to get, all the information goes into sort of a blur and you end up in either the all sorts of hype camp or everything is going to fall apart camp. And I'm going to try to cut through the blur of information and talk about specifics of what's going on, what scientists think is going to happen, and why the information we have sometimes is not adequate for what we really need to make a decision. And in fact, we came out with a paper about a year and a half ago that focused on the fact that the typical sorts of information available from climate science is not really the information that's necessary for decision making. Whether you're a water user in agriculture, water producer, planning district, what have you. So I'm going to share a few images from that paper and also some newer stuff that's come out in the past year that sort of puts some additional numbers to things. So first off, it's getting warmer. No matter where you are in the state, the temperatures have been going up. They're on average about 2 degrees Fahrenheit warmer nowadays than they were during the 20th century. And it's been moving sort of in lockstep with the rest of global temperatures. The graph on the left shows average Texas temperatures in red, dark red, along with a few other global temperature estimates. And the Texas graph is noisier, and that's despite averaging together data over 9 years to get a smoother picture. Problem is when with the globe, everything sort of averages out. And when you zoom in on Texas, you've got lots of variations from year to year just because of how the weather sets up, whether you have an El Nino or a La Nina event present, whether you happen to get a tropical cyclone dumping 50 inches of rain on part of the state. Things like that make the local conditions a lot more variable, and in many ways it's difficult to tell whether there's an actual trend going on unless you've got a lot of solid evidence for it. The sorts of evidence that we look for is really 3 different categories. One is there a clear historical trend? In this case, there is with temperature. Secondly, is this a trend that climate models simulate? If it's in the data and it's not in the models, then maybe it's natural variability, or maybe there's a shortcoming of the models, but it certainly opens up that sort of question. And in this case, the trends are consistent with the model. Most of those global trends I have on this chart are from observations, but one of them, the light blue one, is the average of climate model simulations of global temperature. And you'd see a similar thing if I looked at Texas temperature simulations. And we understand temperatures pretty well in terms of how the science works. That there's more energy being absorbed by the climate system than is escaping to space, temperatures go up. That part is about as simple as climate science gets. With rainfall, it starts getting a bit more complicated. For one thing, rainfall is noisier than temperature. Temperatures are going to change by 1 or 2 degrees on average from year to year at most, whereas with rainfall in Texas, it can change by 50%. We experienced one of the driest, if not the driest year on record back in 2011, and then 2015 was the wettest year on record for the state of Texas. And overall, the trend in central and eastern Texas is upward. It's gone up there, rainfall overall, by about 10 to 15% over the past century, whereas in West Texas, it's been fairly flat. Not very many large changes, but the changes that have existed have been partly up, partly down, and generally not statistically significant. So, somewhat ambiguous trend for rainfall in the historical record. In climate models, they generally predict a slight decrease of rainfall in Texas. So there's a bit of a mismatch there between observations and models, so that makes it unclear what the overall trend really is going to be. Plus the link between rainfall amounts and temperature and climate change is not as strong as it is between temperature and climate change, because rainfall amounts overall are generally determined by weather patterns, and the overall global trend in rainfall is expected to be only about 1 or 2% per degree of warming, with local variations being much, much larger than that. So here we've seen 2 examples of things that are changing in the climate. Temperature, one in which all the ducks are in a row, everything consistent with the direction and the magnitude, and then one with rainfall where different indicators are pointing in different directions. Now let's talk about drought specifically. And the starting point for whether it's going to get drier or wetter is typically what's going to happen to precipitation. I've got that in the category unclear for the reasons I just mentioned, that it's possibly going to decrease, but certainly not certain. On the other hand, the changes in temperature that I spoke of are a drying indicator, because higher temperatures lead to more rapid evaporation. Drought is a balance, represents a mismatch between how much water is coming from the sky in terms of rain and snow, and how much water is leaving the system through evaporation. And if the evaporation rates are more rapid, then the water is not staying in the soil as long, it's not recharging aquifers, it's not running off as much, and what does run off evaporates from lakes more rapidly. So warmer temperatures tend to increase drought. The other things that would point toward drying conditions in the future, changes in rainfall extremes on a month-to-month basis. You can't tease out this sort of thing from the data because there's too much variability, but climate models predict that the variation of rainfall from month to month ought to increase. So there's a little bit of evidence toward that. And also the climate models say that if it's going to dry out, it's more likely to have a decrease of rainfall in the summertime than other times of the year, which would also be bad for drought because summer is when we are most desperately in need of rainfall in general. On the other hand, there is at least one solid indicator that points toward wetter conditions, and that's carbon dioxide itself, which allows plants to be more efficient in their use of water. So on the agricultural side, that means that plants do not need to use as much water in order to grow, in order to extract the carbon from the atmosphere in the form of carbon dioxide. They don't have to lose as much water in the process of exchanging gases with the atmosphere. And then two more things to mention on the unclear category. One of them is changes in biomass, which is as plants respond to a change in climate, does that mean there's going to be more vegetation overall or less? There are good arguments pointing in either direction, actually. The more vegetation there is, the more effectively water is drawn from the soil and into the atmosphere. The last one, changes in rainfall extremes. We actually, scientifically, have a better handle on changes in extreme rainfall than changes in average rainfall. And that's because it gets more closely related to temperature. The greater the temperature, the greater the amount of water that can be in the atmosphere. And when it's raining, the atmosphere, the air above you anyway, is at capacity. It's exceeded capacity. That's why it's raining. And so that means there's more water that can be extracted from the atmosphere and more rain can be produced. And that has an important effect on water supplies, because if you're getting the same amount of rainfall, but it's happening during, more intensely, then that means that you've got greater amounts of runoff and less water soaking into the ground. And we'll see that in the context of climate model projection shortly. Now, to put drought in context, we can actually look at historical drought from tree ring data. This is a box defining West Texas and East Texas for the purposes of the study we did, with the droughts indicating grid points with tree ring data. It doesn't actually mean that there were trees at these points where they got data from. It means that there were trees close enough within a few hundred miles that they were able to estimate conditions locally. And the estimates they came up with go back for 1,000 years or so. Here, we're looking at their estimates of the Palmer Drought Index, the standard measure of drought over the past 1,000 years. And the typical range of numbers for this index is from -2 to +2 for normal conditions. Once you're below -2, you're considered to be in drought. And I've highlighted in red periods where it was essentially averaging close to -2 for extended periods of time, things that we would call mega droughts. There was a paper that came out just recently that made the news that said that Western United States is in conditions that are worse than just about any previous mega drought there. And that's, in that context, Texas is not part of the West. They didn't draw their box to include Texas, looking at average conditions mainly from Colorado to Arizona to California. So it certainly hasn't been as dry here, although we have had periods of drought in the past 25 years. They have been, fortunately, interrupted by periods of plentiful rainfall. Now, before I move on to the projections of this, I want to make a comment about how we think about extremes like drought. Sometimes it'll be said that drought is going to become more frequent. Other times it might be said drought's going to become more or less intense. When you're measuring something like drought on a scale like this, you actually can't have a change in frequency without having a change in intensity, because normally what happens is the average numbers go down, and so you're below a certain threshold more frequently, and the minima become that much farther down as well. So more intense and more frequent is basically saying the same thing, that droughts would be becoming worse if that's the direction of change. And that's actually the direction of change that climate models predict. This is a plot of the average of a bunch of climate models from 1860 to 2100. And the green line, which I'd like to start with, is the soil moisture in the top 30 centimeters of soil, so about the top foot. And It's on a scale so that compared to historical conditions, -1 would be on the dry side, -2 would be a drought. And what this is saying is that by the year 2100, the average conditions, according to climate model projections, would mean that an average year would be equivalent to a present-day dry year. Now, typically, that's about as far as it goes if you got news coverage of things, but I want to add a couple of caveats to that. First off, here's the same sort of plot, but now the bars on the right are representing the middle 50% of climate model projections. So from this, it's clear that most models are projecting a drying condition, but the magnitude of the drying has quite a large spread. Secondly, whenever you're talking about projections, you have to look at what sort of scenario we're talking about. Here in this case, and in most studies like this, we're looking at a very extreme projection, sort of the maximum possible amount of climate change. The purpose of doing it that way is mainly so that it's easier to see what the effect of the climate change is compared to the randomness of natural variability, because the signal gets to emerge from the noise. But when you're interpreting these, you have to sort of scale things back by 30% or 50% if you want to see a more likely scenario. And so that's saying that it most likely it won't be as bad as this projection shows, because this particular projection is unlikely. And I mentioned that when we talk about droughts getting worse, one might imagine this means that the tail of the distribution, the dry end, becomes a lot bigger. Actually, what happens here is the future range of possibilities, which is in red, just the whole thing basically gets shifted for the most part compared to where it is in the present day. And it's not that things are becoming significantly more extreme at both ends. It's just that average conditions are changing. And that means that even calling these droughts is not necessarily the right way to think about them. They're actually changes in the climate. I think it's more appropriate to imagine it, in Texas, our aridity gradient, wet versus dry, goes from west to east. West Texas is dry, East Texas is wet. The change in climate that we're experiencing is not like we're going to get much more extreme weather in the context of droughts. It's like the climate in Amarillo is going to become more like the climate along the Texas-New Mexico border. That's the sort of change we're having, and that's the best way to think about it in terms of the long-term implications. And I'm not saying it's going to be exactly like that border. It depends upon how big the change is as to how far our climate effectively is moving westward, but that's the sort of thing that's happening. Okay, the other results I wanted to talk about that came out more recently is from this paper, same journal, Earth's Future, which is a really cool name for a journal. Even though most of what we say about the future is probably going to be wrong, we're trying. And they looked at the latest climate model projections of these various aspects. So here is the projections of the annual mean precipitation on the left for Texas and the rest of the United States and surroundings. And the colors in Texas are on the yellow side, which is decreases of maybe 1 to 2% per decade. The hatching represents places where less than 3/4 of the models agree on the direction of the change, whether it's going to be increasing or decreasing. And of course, the worst case is 50% agree, because they'll be equally divided. So 75% is still pretty uncertain. So maybe drier, as I mentioned, but not necessarily. Evaporation sort of goes along with it, because you can't have much more evaporation than you have rainfall, because we're limited in evaporation by the amount of water that's available. Okay, soil moisture, consistent with what we saw in our study. The models are unanimous that there should be a drying trend. Here it's a little bit easier to look at the magnitude. We're talking about a 1% decrease per decade in the amount of moisture in the soil on average. And this is, again, with the most extreme climate projection. So scale that back, maybe 1% decrease per 2 decades. It would be the expectation. And then lastly, runoff. The colors here are green, and that relates to the increase in intensity of rainfall. As you get more intense rainfall, you get more runoff and less water soaking into the soil. So the drying for soil moisture and the wetting for runoff is both related to the changes in intensity of rainfall. And there is a lot of crosshatching here in the sense that not all models agree we'll actually get more runoff, but that is the majority opinion from the climate models. And this is consistent with what we've seen. We've analyzed the observations of extreme rainfall in Texas historically, and it has gone up about 15% increase in intensity over the past several decades. So the implications for this for drought can be very different depending upon whether you're depending on surface water or groundwater. And to translate that into what's really going to happen in the future, there's a whole bunch of questions that need to be answered that these climate models don't give answers to all of these questions. First off, what's going to be in the atmosphere? How much carbon dioxide will we have? How big will the overall climate change be? And that depends upon what happens globally in terms of international agreements, technological advances, what have you. Climate models can't help with that. How much does the climate system respond to stuff? Well, that's what climate models are good at. They can say how much warming we'd have per doubling of carbon dioxide, that sort of thing. But then what's going to happen locally depends on changes in weather patterns and so forth. And even though climate models are unanimous, the temperatures will go up. They're clearly not unanimous about the details of the water cycle because of those warming temperatures. And then you have to translate those things into the specific consequences for water supply, for water demand, for recharge, et cetera. And what the models are simulating on the global scale is with the sort of the most rudimentary possible simulations of soil moisture and runoff changes. And finally, on top of all of that, Texas is still going to be in the crosshairs of things like El Nino and La Nina. And what's a 1% change per decade on the short term when we see 20% plus or minus changes in rainfall over decades within Texas because of natural variability. So, yeah, climate change has a long-term trend, but we still have to deal with the short-term variations as well. So what does this mean for groundwater supply? Well, it depends on the sort of aquifer you have. If it's a fast recharge aquifer, then that means the levels are going to depend upon how much the recharge takes place. But slow recharge aquifer, climate change's effect is mainly in the use of the water. The water is drawn out because of demands for irrigation and water supply and so forth. Now, a big water utility at one end of the spectrum, Austin Water, actually commissioned their own studies, did their own climate model downscaling, as it's called, and they're going through version 2 right now to actually improve upon what they did. Conversely, at the other end of the possible spectrum, a small groundwater management district may not have the resources or the expertise to go through that sort of complex multi-year exercise, and the best you can hope for in that circumstance is understanding the direction of change and allowing for some resiliency of the system without having the details pinned down. Now, I'd be remiss without just wrapping up with what the current situation is, because I said natural variability is important. We're going through that right now with the present drought. We have extreme drought across most of the Panhandle, extending on down through parts of the southern plains. And that's partly due to the La Nina that's been present in the Pacific. The La Nina is dwindling. It'll be gone by April probably. But in the meantime, the outlook still calls for decreased rainfall across just about all of Texas. At least the odds are favoring that sort of thing. And it has indeed been dry. Here's a graph of rainfall starting in August for Amarillo. The present year is in green. It only goes up, of course, to the middle of this chart, but it's like second lowest in history over that period. And if we don't get another 2.5 inches of precipitation by the end of March, it would also still be lowest in history. So that's the drought we're dealing with. Fortunately, most of those resolved themselves with plenty of rain in the springtime, but not all of them did. You can't have a long-term drought without starting with a short-term drought, and unfortunately, that's what we're starting with right now. So I'll leave this up as a summary and details on how to get hold of that paper, which is open access, and my email for further information if you want to follow up. Thank you.